All right, welcome back, ladies and gentlemen. We are continuing our discussion on our relationships between parametric equations and vectors and parameterization and things of the nature like that. And so in this video, we are going to specifically be discussing how to write a vector equation. We're going to talk about parameterizing a line, and we will also be discussing eliminating the parameter. So first and foremost, I want to thank our other pre-calc teacher over at RHS, Ms. Hines, for this example here. It is kind of a great opener into a couple of the other examples that we have in our book. So that's why I wanted to go ahead and make sure that we talked about these examples that she created. So first and foremost, let's kind of talk about a vector equation first and foremost. We've talked about parametric equations so far, and obviously remember that was taking our x and our y components and having a separate variable or a different parameter, right, that results in the x and y components. And we're going to kind of utilize a little bit of that same concept there. But we're going to talk about a vector equation first and foremost, what it is and how can we write it. So what we're looking for first and foremost for a vector equation, now usually R or V is kind of that universal signal for writing a vector. And so if you want to just write R for the resultant or V for vector, either one, it ends up being understood. And so when you kind of think about this vector equation first and foremost, we want to actually ask ourselves is, how does this kind of relate to a basic equation of a line? Well, think about when you're doing an equation of a line, what do you need? Well, you need the slope of the line, and you need at least one point that lies on that line. And so that's going to be kind of what we're looking for. We're going to be looking for what is the position of this vector, and then what is the direction of the vector as well too. So when we are writing a vector equation, we are looking for the position vector. Remember, the position vector is going to be kind of at that standard position at the origin. All right, and then we're going to add the directional vector to that. So from the first point, it'll kind of tell you what is the direction to get to the second point. All right, so that's kind of what we're looking for. All right, however, we need to kind of take into account that that direction vector could have some kind of scalar on top of that. So you could be given 2 points like we have here in A and B. Well, what if they gave you a random arbitrary point past point B, for example, right? You would have to know what that parameter would be to get to that point. And so we're going to add a little t being multiplied as a scalar to that direction vector. And that's going to kind of help us show what the parameter of the direction vector is going to be. And so in this example here, we have write a vector equation for the line through point A, which is at 1, 3, and B, which is at 3, 8. So I'm going to go ahead just real quick and just put those into perspective for us. So we have 1, 2, and 3 right there. And then 1, 2, 3, 4, 5, 6, 7, and 8. So we are at 3, 8 roughly, right? So there's B, there is A, and for our line, something of the nature there. Now I could be off a little bit as to where that goes exactly, but that is okay. It's just for visual purposes as of right now. So let's talk here first and foremost. If I were to make, if I were to make this vector equation, well, what would the position vector be? Well, remember, the position vector is going to be at the vector OA, right, or the origin, right, to get to A. So that's what's going to kind of tell us where does this vector begin? What is the standard position of this vector? So we're going to be looking at vector OA for this specific one. And then for our vector, that's going to give us direction. Well, once we are at point A, then the question is, well, how do I get to point B or to any point past that? So that's what our direction vector is going to end up showing us. So I want to know what is the direction to get from A on to B. So that is going to be our direction vector there. And I'm still going to multiply it by that parameter or that scalar. All right, so now in this example, what is the position vector? Well, remember, if A is at 1, 3, right, and the standard or the initial point is going to be at the origin, 1 minus 0 is just going to be 1, 3 minus 0 is just going to be 3, so that means our position vector is just going to be at 1, comma 3. And I'm going to add that to our direction vector. Now, this is where it gets a little trickier. Some people automatically will assume that it is going to be at that 0.38. That is not the case. Remember, it is going to basically be how do you get from A on to B? That's what we're asking for, is how do you get from A on to B? So if we're looking in that case here, we're going to say 3 minus 1 is 2. And if we go from the y component, we're going to say 8 minus 3. And that is going to be 5 being multiplied by our scalar or parameter t in this case. And so at this point, this is our vector equation. You might also kind of see it written as the component x comma y is equal to 1 comma 3 plus 2 comma 5 times the parameter t. So then how can we utilize this in parameterizing a line through, let's say, for these specific points to keep things consistent? Well, first and foremost, let's go ahead and think about what we were trying to do by parameterizing a line. We are trying to find out what the actual x and y equations are going to be for the same scenario that we just posed. So let's go ahead and take a look at what that could be. So if I'm looking at my x equation, so well, what is that x equation going to be? Well, if I'm adding these two vectors together, I am adding the x components and I am adding the y components. But remember, this was distributed to both of them. The parameter was distributed to both of them. So I'm really going to say that it's 1 plus 2t. And then the y components would be 3 plus 5t. And then the question is, well, what are the boundaries of t? Well, in this case, t is going to have all real numbers, right? So t will be in all real numbers because it's a line. It's going to go off into infinity in both directions there. And then the last thing that I want to talk about in this example is, well, what if you want to just completely eliminate the parameter and write it as a normal Cartesian equation? Well, that's just basically going to go ahead and take us into account of what we're looking for. If I go ahead and solve for t using my x equation, I can go ahead and see that t is going to equal x minus 1 divided by 2. And so then if I resubstitute that into my value of y, I can say that it's 3 plus 5 times the quantity of x minus 1 over 2. And just to simplify that into some actual slope-intercept form here, we get 5 halves x, and then we get minus 5 halves. And just to kind of simplify that out here, we end up getting 5 over 2x, and then 3 minus 5 halves will get us 1 half. And so that's how we can kind of see that there. Now, before we close, I want to kind of just show some relationships here in especially this Cartesian equation in regards to the vector in the beginning, the vector equation in the beginning. So if you remember kind of correctly, when we're talking about our direction vector, that direction vector, really is the change in y and the change in x. That is what the x and the y components are when it's all said and done. And so if you kind of think about what's happening here, take a look. When I say change in y over change in x, what does that kind of remind us of, maybe, if you will? Well, hopefully you kind of remember that that's all about our slope, right? Change in y over the change in x is our slope, right? So 5 halves. Well, take a look at this direction, guys. The change in y over the change in x. So it's kind of cool how they have some relationships there. And then, well, where do we come from in terms of our position vector? Well, if I kind of go back to the very beginning and I write this equation of this line right here in point slope form, you end up getting y minus 3 equals 5 over 2 times x minus 1. And take a look. You end up getting your, whoops, didn't want to erase it, wanted to highlight it. You end up getting your position vector here and here, 1, 3. So it's kind of cool how they kind of all relate in the end as well. So hopefully this was a good kind of opener question. We defined what a vector equation was. We kind of showed what the basic standard form would end up being. And then from there, we parameterized a line using our new vector equation. And then last but not least, we eliminated